title of today's talk is, as you can see, fantastic games and how to win. Well, it's kind of misleading because I won't really teach you how to win a game. Okay, we'll do something about that. So, first of all, what I would like to ask you that what do you understand when I say the word game? Anyone? Any examples of a game? Rock, paper, scissors, fine. Anything else?
BGMI.
BGMI, fair.
Chess.
Ludo, chess, yeah. So these are all games. Now, can you find something that is common in between them? Chess, Ludo.
There are players and players, separatists.
Somebody wins, somebody loses. Okay. Yeah. So what we got out of this is any game can be characterized by players, rules, and outcomes. Not necessarily, I mean, when we think of a game, we think of win or lose, but it is some kind of outcome, some kind of payoff that a player gets. Okay, so game theory, in essence, so whatever English I have written here, it's just the definition of a game. That a game is, in essence, interaction among players. Now, who are these players? These players are decision makers. Any people, any environmental factor, any organism which can make a decision or which we can attribute to making a decision. So, a game is the interaction among these decision makers, and the outcome for each player depends upon the decisions made by the other players. So that is the way in which they interact, and that is what we call a game. And the study of this is what we call game theory. Okay, so these are certain terms and conditions. Players, well, we all know, I won't describe anything else. Payoff is what any player gets in the end. Suppose you are gambling. Okay, so you wish to get something at the end. We don't know whether you will get it or not. So whatever you get or whatever you don't get, that is your payoff. Each player has a separate payoff. For example, someone said chess. So in chess, a payoff will be either you win or you lose or you draw. These three are the possible payoffs. And the other thing that I would like to familiarize you with is strategies. So what we can say strategies in a layman's language is basically in every node of the game where you are to make a decision, the set of all decisions that you make or the set of all actions that you take when you are to make a decision is something that you call strategy. I would explain strategies further as we go along. Right now we need just these English definitions of these terms. Okay, and there are certain conditions that I would like to tell you beforehand. First of all of these games that we are going to see in this presentation at least are finite. We will not talk about any infinite games. There may be, but we won't. The payoffs that we see, okay, these payoffs can be essentially represented by a function. What is that function? What is the domain? How does that function look like? I will describe that later. These are real values, and the players are rational. So what do I mean by rational? Rational means that they aim to maximize their own payoff given their values and beliefs about the other players. So as a player, at least in these kind of games, you are not concerned about what the other players, what are the payoffs of the other players. So let's say there is some game and there are two different outcomes. Say two players and there are two different outcomes. In one outcome, player 1 gets a payoff of say 2 and player 2 gets a payoff of 4. In the other outcome, player 1 gets a payoff of 2 and player 2 gets a payoff of 1. So for player 1, both these outcomes are indistinguishable. For him, it's same because he gets 2. It does not matter to him whether the other person gets 4 or 1. So there's no bias. Okay. Now I would start by showing you an example of a game. Okay. So let's consider this. Can everybody see whatever I am writing or drawing? Just let me know if you have any problem. This is a grid. Okay, so this is a certain kind of grid, and there are two players, player 1 and player 2. So what happens is player 1, he starts the game. And regarding rules, this game goes as follows, that player 1 first chooses a square. So player 1 and player 2 choose square alternatively in each turn of the game. Now, if any player chooses 2 or 3, then you cannot capture 4. Okay. So say I am player 1, in the first turn I choose 3. Then player 2, for player 2 the choice of 4 is gone. So he can either choose 1 or 2. Similarly, if I choose 2, then 4 is gone, I can choose 1 or 3. Now, the game ends when square 1 is chosen. And whichever player chooses this square 1 loses. Okay. So, yeah. So this is the example of a game. This is the example of a game of how we tend to describe it to each other. But then if you want to be more mathematical, then, well, you need to formalize this notion of a game. You need to formalize it in terms of mathematics or logic or whatever you want to say that is. So, we can describe this game. He is the starting player, right? Okay. How many choices does he have? 4. I mean, 1 is also a choice. It might be the losing choice, but it's also a choice. I can write this as. Fine. Now, what happens if he chooses 1? Or I can write it as 2 wins. I mean, either way it's the same. If he chooses 2, what happens? The other guy will get this, right? So, now, after 1 chooses 2, what choices does 2 have? There are 2 choices. Right? Similarly, here we have, right? Okay, so if 2 chooses 1, 1 chose 2, 2 chooses 1, then 2 loses, right? So 1 wins. If 2 chooses 3, then again the next player who would make a decision would be 1. So what choices does 1 have? Only 1. Right?
So, like after choosing a square, the other player doesn't have the option to choose a square after someone chooses.
No. Sorry. I should have mentioned this. Once you choose a square, it's gone. So if player 1 chooses 2, then player 2 cannot in any instance of the game choose 2 again. Okay. So similarly, we can draw whatever this is and we can come to a conclusion. So what I did was I represented this game as a mathematics or as any structure. So what this structure is, if you know, if you have studied either CS or maths, you would know that this is a tree. Okay. In math or in CS we call this a tree, specifically a rooted tree with one root, and then these things are called leaves. Right? Okay. So, yeah, so this is basically, you don't need this. Okay, so in mathematics, we define any game, and this might look a bit scary, but it isn't. You don't need to go into the intricacies of this. I will just say what this means. So we represent the game as this tuple. What this tuple is, the first set that is n is basically the set of players. In this case, we had player 1 and player 2. So this is n was 1 and 2. These three things represents the tree. Okay. You don't need to know what V X naught is right now. X naught, just know X naught is the starting root. The root that is 1 in this case. Okay. Vi is a partition of this V. So this tree had certain vertices, right? These were the vertices. 1, 2, 3, 4, 5, then again 6, 7. So these vertices can be partitioned. Okay, so specifically these were the non-leaf vertices. What do I mean by, okay, so notice one thing, that whenever we reach a leaf of this tree, the game ends. So leaves are basically the terminal, the outcomes of the game. So if you take the set of vertices and you take out the leaves from there, what remains are a set of decision nodes, are a set of vertices where each player needs to make a decision. Okay, in the first, in this vertex, one can make 4 decisions, he can choose among 4 decisions. Similarly here, this guy can choose among 2 decisions, and so on and so forth. So these decision vertices can be partitioned, in this case, to V1 and V2. V1 would be the set of vertices where the player 1 makes a decision, and V2 would be the set of vertices where player 2 makes a decision. Okay, fine. O is the set of outcomes, and U is basically the assignment of an outcome. So U of this leaf is that 2 wins, U of this leaf is that 1 wins, so on and so forth. So if you are comfortable with this, then I would further tell you about what I meant initially by strategy. This thing. So this thing maps the leaves. What are the leaves? The leaves are the terminal positions of the game, the places where the game terminates. So whenever my game terminates, I would have one of some outcome, right? So my game only terminates when I have a certain outcome. In this case, it is either 1 wins or 2 wins. Fine. So this, if I say that this vertex is, say, L1, the leaf 1. In U, the function U maps L1 to 2 wins. It maps L2 to 1 wins. This is an outcome, this is an outcome. There are only 2 possible outcomes of this game, either 1 wins or 2 wins.
So, how does this leaf 2 means?
I am calling this as leaf 1, this as leaf 2, this as leaf 3. I am calling this arbitrarily. I mean, so it maps, the function U maps every leaf to a certain outcome of the game. Okay. Everybody is fine? Okay. So strategy, what I said about strategy was that some player, I mean, in the very English language sense of the definition, you understand the strategy to be, some kind of a plan to play the game, right? So how we talk about strategy mathematically is that a strategy is a set of actions. It's a mapping of actions rather. So say the strategy of player 1. would be in his first decision node, he can choose these four choices, right? Any one among these four. He will choose one of that. I mean, some of either one or two or three or four. So that would make a part of that. The strategy is a tuple. Strategy is a tuple, and that tuple has all of player, say strategy of player 1 would have all the decision nodes of player 1 coupled with what action he takes at those decision nodes. So my strategy, if I have a certain strategy, say S1, I am player 1. So my strategy would tell me that when you are at this decision node, choose this or this, whatever it is. Then again, when you are at this decision node, here basically you have one choice, but if you had two or more choices, then choose this. So my strategy will specify which actions I should take as the game progresses. And it is like, it's not, what I mean to say is that it's a complete, or rather, so it traverses the whole game tree. What I mean is, there will exist no point in this game when I don't know what to do next. That is what I mean. So at every point I know that my strategy specifies to me that what I should do. Okay? So now probably someone said chess when I asked about the examples of a game. So I hope everybody knows chess here. Well, do you know? Okay, what do you think? That is chess a finite or an infinite? Right, it's finite. So we might not know how many moves or how many plays it takes, but it ends somewhere. It ends in three outcomes: either black wins, or white wins, or it's a draw. So stalemate and insufficient material, all those are considered to be a draw. Do you know that how many possible board positions can there be in chess? Do you have a rough idea of how many possible board positions you can have in a chess game? If you don't know, well, there's a number, I forgot the name of the guy who gave this. So it's approximately 10 to the power 120 or something. Approximately. Now, just to get a sense of how big this number is, the estimated number of atoms in our universe is around 10 to the power 80. So let that sink in. But in case of chess, so why I said this was, in game theory we have developed things that make sense of these impossible things and make them look trivial. So, okay, is chess solved? Like, do you know how to win any chess game? Not yet. Okay. But in fact, I would say it is solved. It is solved. Now, bear with me. This next theorem that was given by one of the founders of game theory, von Neumann, says that in any finite two-player game, okay, forget perfect information for now, I'll be more descriptive of this. With these outcomes only, like if you have a game, it's a two-player game, and your outcome can either be that player 1 wins, or player 2 wins, or it's a draw. There can be no other possible outcome. And the game is finite, and that game has no elements of chance. So there's no tossing of a coin, there's no rolling of a die or picking a card, nothing of that sort. Then exactly one of these three things is true. So either player 1 has a winning strategy, or player 2 has a winning strategy, or both players have a winning strategy that guarantees at least a draw. So what this means is that when you play chess is a two-player game. Okay? Chess has no chance to win. And chess can have only three outcomes, which is either white wins or black wins or a draw. So by this theorem, we know that either white, the person playing white has a winning strategy, or the person playing black has a winning strategy, or both of them have a strategy guaranteeing at least a draw. So you can prove this, but the interesting thing about chess is that you know one of these is true, but you don't know that which of this is true. So I would say that the game of chess is solved. We just don't have enough computational power to compute that which of this is true. I would not want to go into the proof of this theorem right now, but if we have time left and if you guys are interested, then we can do the proof of this later on. Okay. Now I would make you play a more simple game that would related to the earlier game that we call the game of Chong. This game was given by David Gale, and yeah, so the rules are that you have a rectangular bar of chocolate. Okay, this bottom left black and cross square is poison. Similar to that simple game that I described here, if you choose one square, so player 1 and player 2 chooses one of these squares alternatively. If you choose say this square, then the top and right, either the top squares, the squares in the right and the squares diagonally, so basically if the square coordinate is I comma j, assuming this is my origin and basic axis, so if ij is eaten, then greater than I and greater than j squares are also eaten. So you can't choose them anymore. So if I eat this, then this whole block is gone. So now I have this thing left. Does everybody understand that? So now similar to that game, whoever eats this loses and the other guy wins. So yeah, what do you think? That does any player okay, player 1 plays first, player 2 plays second. Does any player have an advantage? Who does?
The one who starts the
Okay, fine. Good guess. So yeah, player 1 actually has a winning strategy. And okay, this is a very interesting proof. So suppose, okay, don't go in this, I'll just tell you what this means. Suppose one does not have a winning strategy, then player 2 has a winning strategy, right? Okay, notice that this game also has two outcomes. Either one wins or two wins. There is no draw, but it's still, that thing is still allowed by the earlier von Neumann's theorem that we did. So in this case too, we know that either player 1 has a winning strategy or player 2 has a winning strategy, or both of them have a strategy guaranteeing at least a draw. So let's assume that player 2 has a winning strategy. Okay, in this case, the draw thing does not make sense because there is no draw. So only either player 1 has a winning strategy or player 2 has a winning strategy. Let's assume that player 2 has a winning strategy. Okay. So in that case, what it essentially means is that no matter whatever square player 1 chooses, player 2 can follow his winning strategy and win. Right? In particular, if player 1 chooses, so this bar is m cross n. So if player 1 chooses this top rightmost square, that is the coordinate, okay, n comma n, then even in this case, player 2 should have a winning strategy as per our assumption, right? So in fact, that winning strategy will give him exactly what square to choose next so that he can win, right? Say that is some I0 comma j. Now when he chooses I0 comma, okay, so when n comma n is chosen, only this square is gone because there is nothing to the right or top of this. When I0 comma j0 is chosen, this whole portion is gone, right? So here what we have is that this can be seen as a new game. Okay, not exactly as the previous one, but this is a kind of a sub game of what we described as original. So So here, notice that whatever move again player 1 plays, player 2 has his winning strategy. Like if I call player 2's winning strategy as S2, then he can follow this S2 to win. But if player 1 had chosen this I0, J0 as his first move, then player 1 would have won, because if player 1 would have chosen I0, J0 as his first move and then followed the winning strategy of S2, then anyways player 1 would have won. Right? So what this means is that if player 2 has a winning strategy, then player 1 also has a winning strategy. Is everybody with me? But right now we saw that player 1 and player 2 cannot have a winning strategy at once. So our assumption was wrong. Player 2 does not have a winning strategy. So the only option that we have left is that player 1 must have a winning strategy. This is something that we call the strategy stealing approach. In this case, I would go back to this theorem. In the game of Chong, we had in the game of chess, we proved that we can prove that one of these three things is exactly true, but we don't know which of this is true. In the game of Chong, we proved that player 1 has a winning strategy. But the interesting thing is that for a general M and N, we do not know how to calculate this winning strategy. In fact, even if you assume the simplest case of N is equal to M.
I have a doubt in that videos.
This
Here,
one?
here how do I know that the piece which player 2 chooses is in the center, means it can be in the other corner, right?
Yeah.
Then the top corner will not be like separated.
You mean this to be here, right? Here. Say I0, J0 is here.
In the bottom.
Here.
Right. Here also.
Even in that case, this would always go
No,
out.
if it is in n, 0, then
N, 0. Here.
Huh?
Even still, this is at the top. This, okay. So notice one thing. No matter whichever square you choose, here, this square always goes up. Because it is the, like, any ij that you choose, I is less than equal to m and j is less than equal to n. So your n comma m would always go out. So that is the reason he plays that trivial move, so that he can then steal his strategy. Okay.
Can you repeat how did you get that player who does not have a winning strategy?
Okay, so we showed, are you convinced of this fact that if player 1 plays this as his first move instead of playing this,
Yes.
then player 1 has a winning strategy. He will just imitate S2. He will follow S2. Okay. So follow S2 in the sense, here one thing I should make clear that S2 is not a private information. So it's not that only player 2 knows S2. We are assuming that this is a public information and you can imitate whatever strategies you want. So player 1 first chose this, then
Can we see that there is a given set of strategies from where if I choose a particular position, I have one strategy with regard to the position.
yes, yeah. So basically, what a strategy means is that so given any m comma n, if you have enough computational power, then you can by brute force calculate all the possible strategies. So there is no strategy that is unknown to you. So here player 1 just imitates player 2's strategy to win. So what we came to the conclusion that if player 2 has a winning strategy, which was our assumption, then player 1 also has a winning strategy. But just now we saw in von Neumann's theorem that these two cannot happen together. That means our assumption that we assumed was wrong. It's a contradiction. So if our assumption was wrong, then player 2 does not have a winning strategy.
What do you mean by player 1 is like copying the strategy of player 2?
Okay, so copy in the sense is S2, the strategy S2 basically describes that if you are to, in this case specifically, if player 1 chooses some square or something, so wherever you have to make a decision, strategy 2 specifies that what decision you should make. In this case, wherever you have to choose a square, strategy 2 gives you explicitly which square you should choose. So that is what I mean when I say player 1 imitates. So player 1 follows the strategy that player 2 had. Okay. So in fact, if you take the simplest case of n equal to m, we still do not know what is the winning strategy even for numbers like n equal to 30, 35, 40. So that is how complex it is finding the correct strategy. When you can prove that it exists, but you can't find it. Okay. Yes. So notice one thing, that when I said von Neumann's theorem, I specified that it had perfect information. So what I mean by perfect information is that all of these games that we saw, here both of any player knows whatever he has, I mean he will obviously know whatever he has played during the game, but he also knows whatever player the other player or the other players have played in the game. Right? So when you are playing chess, you can write down whatever moves your opponent makes, and at any point you know whatever has been played up till now. But well, this is a very restrictive assumption. So there are possible games where you do not know how, like what are the choices or what are the moves that has been made by your opponent. So for example, we have the game of matching pens. So what this game states is that, again, there are two players. So okay, by the way, all these examples are of two players because it's very easy to compute. So I have taken all examples of two players. There exist games with more than one players, with n players, everything. Okay. So here what happens is that player 1 and player 2 both choose a side of a coin. Notice that this is not tossing a coin. I am not tossing a coin and randomly choosing. I am given a coin and I say that okay, I choose heads or I choose tails. Player 1 chooses a side, player 2 chooses a side. If they match, if their choices match, then player 1 wins $1 from player 2. If their choices are distinct, then player 2 wins $1 for player 1. So we can describe this game as this. Forget this ellipse one. Player 1 has two choices, heads or tails. Whichever choice he makes, the next decision lies with player 2. Right? He has again two choices, head and tail. Now if they are matching, then this is the outcome. Similarly, they've given the outcome. Fine?
So why is it different from tossing both the coins and noting the results and then moving on?
No, tossing both the coins means that you don't, like, you can either have heads or you can either have tails. It is not your choice to make. It is, okay, so essentially what I have omitted in this whole presentation is a game which is a type of games which are called games with chance. So whenever you are having an element of chance, I toss a coin or I draw a card. So there, the choice does not lie with you. The decision, you are not the one making the decision. In that case, what we do is we include a third player in the game, which we call player 0 or the nature. Nature makes the choice for you. You are not the one deciding it. So you don't have control over what choice you have. But in this case, you do have control. You might not know what player 1 chose, but you do have control over whatever you are choosing. That is the difference. Fine? So, in this case, basically, for player 2, okay, here, when we had this game, so in all these vertices, player 2 knew that exactly which vertex is the game right now in. So at this point, player 2 knew that player 1 has chosen this 2. But in this case, player 2 he knows that player 1 has made a choice, but he does not know that which choice has he made. So in that case, we draw this ellipse around these two decision nodes and we call this an information set. So he knows that the game has reached this point, but he does not know which one. Also notice that in case of information sets, the actions that you need to take are symmetric for unlike the same. So if you have n vertices in this information set, then the actions that you can take in each of these n vertices are the same. Otherwise, this does not work. Okay, so in this case, yeah, so this is what we call something with imperfect information. Yeah.
Like if player 1 for suppose like tosses the coin or chooses anything, will it change? Do you think will it change in the probability of player 2?
Yes, it will. I will give you an example. Okay, for example, if you remember the game of Chomp. So in Chomp, okay, one thing if you remember that when I stated von Neumann's theorem, I specifically mentioned that there is no element of chance. So we applied von Neumann's theorem to say that okay, player 1 has a winning strategy in the game of Chomp. Now say I modify the game of Chomp. How do I modify it? Before my game starts, the two players meet like in a cricket match and they toss a coin. The one who gets heads, like the one who chooses heads, gets to start the game. So in that case, can you apply von Neumann's theorem? You can't. So that is how your play changes. In that case, if player 1, so that choice matters. Like the element of chance matters. It changes the game.
In that case, can't we apply von Neumann's theorem in each case?
Yeah, you can apply it in each case, but then, well, your definition of player, you can't say that for the whole, that, okay, these outcomes or these theorems, whatever we stressed until now, are for the whole game. So in that case, you can say that player 1, yeah, in this case this happens or in that case this happens, but you can't say that in general for every instance of the game. That depends on what chance, like whatever, it's a 50-50 chance.
But will there be a winning strategy in a game of chance?
Yes, there can be, but it's just not described by the von Neumann's theorem.
How is there a winning strategy in like a toss?
I'll come to it later. I'll come to it after I finish this topic. Otherwise, we'll get diverted.
Like what I was saying for like tossing coin was like only specific for this. Like for suppose if I'm player 2, then for me also I'll have that will that face with the head or tail is 50-50 for me. Doesn't matter that player 1 has like tossed the
Yes.
coin.
Okay. So what happens in a game of choice is that these outcomes that we are talking about, right? These outcomes or these strategies, they change. So the definition of the thing strategy changes in a game of chance. Here, your strategy describes explicitly that which action you should take in which vertex. In that case, it will a strategy will give you a probability distribution over the decision vertices that you have. So that is how the game changes and that is how the description of the game changes. Okay? Yeah, so these are basically the rigorous math definitions. I won't go into these. So, this is in the case of imperfect information, we slightly change our notion of strategy such that it's no longer going from a vertex to a action. It is going from an information set to actions. Okay, so because you don't know which vertex it has reached, so you define your strategy on the whole of that ellipse that we meet. Okay, so now all of this time we represented our games as a tree. Well, this is helpful, but this is also too much information. I mean, not that that's bad, but it's just too much to handle. So in this case we had the sequential structure of the tab. But you might argue that okay, fine, but in some cases we might not need this much information. What will I do knowing all the all the possible 10 to the power 120 chessboard combinations? Yeah, I'll come to that. So in that case, what happens is you have an equivalent form of representation of games, which we call strategic form games. So previously, all of these were extensive form games, or the extensive form representation of games, where we draw a game tree and we represent it as such. For strategic form games, you don't need all of that. You just need your players, you just need your payoffs, and you just need the set of strategies. So that ugly looking 8 or 9 tuple thing that we had reduces to a 3 tuple. I'll come to exactly what that is. Before that, who said rock, paper, scissors? Someone said. Okay.
I have a doubt. Like in rock paper scissors, it is simultaneous. Like the previously games you mentioned, it wasn't simultaneous. First,
No.
a player
In the game of matching pennies, it was simultaneous. Or what a simultaneous game means is that you have imperfect information. That I don't know what you are going to do, so I don't have any information of what you have done. Rock paper scissors, you and I play a rock paper scissors game over here, is the same as you are there in M2 and you choose either rock paper or scissors, and I am in M1 and I choose rock paper or scissors. We don't know what we choose. So that's the same thing. So essentially, rock paper scissors is a game of imperfect information where one player does not know what the other player is doing. So as I mentioned, that this is how the representation of the game looks. Right?
Differentiate between imperfect information and probabilistic,
Can I do that after this? After I am done with this, I will tell you exactly what that is. Okay. So we essentially might not need this thing. We can represent it as a strategic form game like this. So here, what are my strategies possible? So if you and I are playing, I have 3 possible strategies: either choose rock or choose paper or choose scissors. You have 3 possible strategies. So we can represent it as a matrix, as a 3 cross 3 matrix. So these combinations, if you are rock, we assume it's a draw. Rock, paper, well, paper wins. So if you win, I have given it a 1, and if you lose, I have given it a minus. In case of a draw, both get 0. So this is an alternate representation of rock, paper, scissors. Now, something that I would say, that in this case, see, there are 2 players. So this is a matrix. If you had 3 players, it would be a 3D matrix. If you had n players, it would be an n-dimensional matrix. Okay. So yeah, that was one thing. I would go to the definition. Yeah. So in the case of strategic form, you have 3. It's a 3 tuple. So n is basically your set of players. Si is all possible strategies. That might be infinite, but it's fine. Ui is the payoff function that we described in the first representation as well. Okay, so is everyone with me? Now, I would go, we talked a lot about definitions. With this I would proceed to the most interesting notions of game theory, of fundamental game theory at least. One of it is called dominance, and from dominance we go to something which is very popular and is known as Nash equilibrium. Okay, so this is a certain notation. I will familiarize you with this a little later. You don't need it right. So let's consider another game. I have so player 1 has, player 1 chooses a row and player 2 chooses a column. There are 2 rows, there are 3 columns. as you can see, T and B for player 1 and L and R for player 2. Now, this is something that is very easy to demonstrate dominance. Consider player 1's okay, so here player 1 has two possible strategies, choose T or choose B. Player 2 has three possible strategies, choose L, choose M or choose R. Right? Okay, so if player 1 chooses T, okay, then I am comparing M and R. Fine. If player 1 chooses T, then player 2's outcome if he chooses R is 2. Okay, so the first thing here is player 1's outcome, the second thing here is player 2's outcome. So for M, player 2 has an outcome of 2, for R, player 2 has an outcome of 1. So if player 1 chooses T, then the better strategies among these two for player 2 will be M. Right? If player 1 chooses B, then player 2 with M he will have 1, with R he will have 0. So in this case too, M is a better strategy, M is a better response to player 1. So you see, no matter whatever player 1 chooses, player 2 is better off choosing M than R. In this case, what we say is that strategy R is strictly dominated by strategy M. So what this means in terms of payoffs is that no matter if SI is a strategy that is strictly dominated by TI, in that case SI was R and TI was M. Okay, so no matter whatever the other players choose, your outcome when you choose TI is greater than your outcome when you choose SI. Is this fine? Like, is this notion of dominance fine? So no matter whatever the other player chooses, if you have 2 or 3 strategies and one of them dominates the other, it means if you choose that dominant strategy, you will always have a better outcome. Similarly, we have the notion of weak dominance. Okay. Now, so
in the previous case, M does not strictly dominate strategy L, right? Because
no, not L.
Yeah.
It strictly dominates strategy R.
But L it does not strictly dominate.
No.
Because you are getting an output payoff of 3.
Yeah. L in fact, L and M, neither of them are dominant. So neither does L dominate M, nor does M dominate L. So what I mean is that if you remember in the very first terms and conditions slide that I showed you, I stressed the fact that your players are rational. So if you are a rational or a smart person, you would always choose a strategy. You would never choose a strategy that is dominated by some other strategy. Because you know you have a better choice, so why would you? So we can do something which we call the iterated elimination of strictly dominated strategy. So in the previous case, we can eliminate R because a rational player again, he won't choose R over M or L. Okay. So yeah, because of this fact that I stated that a strictly dominated strategy is never a best response to any strategy that your other player plays. For in that example, no matter that player 1 played T or B, R would never have been a best response, right? Because it was dominated by M. So if each player, what we say is that if each player has a strictly dominant strategy, the outcome, in that example this does not work, but if you could have possibly eliminated, if your strategies would have been such that you could eliminate all the other strategies and you would be left with one strategy that strictly dominates all your other strategies, then well, if this happens for both the players, then you would have a unique outcome of the game, always, because you would always play that dominant strategy. You would never choose a suboptimal thing for yourself.
So the previous case was the case of weak dominance.
No, no. The previous case was not a case of weak dominance. So dominance depends upon strategies. It's not dependent upon game. In this game, M strictly dominates R. So you can, by the process of iterated elimination, you can eliminate R. Okay, because you would never choose R over L or L for that matter. Okay. So in this case, if you do an iterated elimination, you will be left with L and M. Okay.
Show with how do we claim that something is true.
In this case, consider just M and R. Okay, so we are comparing these, so we only consider the payoff for player 2. Fine? Now player 1 can play either P or B. Okay, so if it's P and M, player 2's outcome.
P and B are moves.
T and P are moves or strategies. In this case, you can say move strategy. In this case, it's both the same thing because he is only choosing a row. So he will either choose T or choose P. For this game, if you were in a game where it was not, it was not this simple, then you would map strategies in this manner. Like the strategic form that I showed, for example, in rock paper scissors, you had 3 rows, so you had 3 strategies. So even in that case, you could have done something like this, but the thing is, stone paper scissors does not have a strictly dominant strategy. You can see it in that matrix itself. So see, if there's T and M, then the outcome for player 2 is 2 and 1. Then it's 1 and 0. So in any strategy that player 1 plays, player 2 is always better off playing M than R. So in this case, we say that R is L. Does not matter. Doesn't matter because you would never choose R. If R is strictly dominated by one of your other strategies, you would never choose R. Right? I agree that it is not strictly dominated by L. But see, for L, in the case of B, you would be better off choosing L. In the case of P, you would be best off choosing M. So in any case, you would never choose R. So it's just a simplification of the game to eliminate R.
Is it M a more safe strategy?
Isn't M a more safe strategy?
Like
One is high risk, high win strategy, and one is safe strategy. The type of strategy is different.
So, okay, you are saying. So the thing is that depends on the preference of that player.
Exactly. If we disregard consideration that player is a rational player, then we can say he should always go with M.
No, if you disregard that he is a rational player, then he can go with R.
He can go with art. I mean, a rational player is not
Why? If player 1 plays B, then you should go with L. So a rational player always tries to maximize his outcome. So in this case, we have a situation where R will never give him the best outcome. So we are eliminating R. That is the essence of this. So okay, this I'll come to this maybe.
Not selection.
Yeah.
By this way, elimination of strategy, not selection of strategy.
No, we are eliminating strategies that you would never use.
But not select by.
No. Okay. Probably each and every one of you have heard of this. This is a slight variation on my part that the game is I have simplified the game to the fact that you are caught cheating in an exam, and well, I mean, cheating in an exam in the sense you are not caught in the act, but you are caught later that oh your wrong answers match probably. So in this case, okay, so in this case what happens is that if both, so player 1 and player 2, you and your friends. So if both of you are interrogated, fine. If both of you confess, both of you get suspended for 1 semester. If neither of you confess, well, you just get detention and you are let go because there is no evidence. If one of you confess, then the one who confesses goes free, and the one who does not confess is expelled. So we can map this in the strategy form as this. So -1 is associated with
1 semester more.
sorry. No, -10 is rusticated, -5 is 1 semester long. Sorry. -1 is 1 semester long and yeah. Fine. And yeah, okay. Yes, fine. -1 is just you get a detention, and -5 is that both of you get a suspended for a semester. Okay. So in this case, if you apply that concept of dominance, so you are thinking about yourself and you see that if your opponent is silent, you are better off confessing. If your opponent is silent, then if you stay silent, you get -1. If you confess, you get 0. So you are better off confessing. If your opponent confesses, then if you stay silent, you get -10. If you confess, you get -5. So even in that case, you are better off confessing. So your dominant strategy, your strictly dominant strategy is that in any case, you should confess, right? This is something that corresponds to a fact of Nash equilibrium. You guys might have heard about John Nash, and he gave this really interesting concept. Okay, by the way, I would like to say something, that this is not the eliminating strictly dominated strategy is not how you arrive at a Nash equilibrium in a general game. For this specific game, there is only one Nash equilibrium, which is this. So you got it by eliminating strictly dominated strategies. For Nash equilibrium, what you do is you analyze each of these tuples. Say for this, okay, so I would go to the definition. Okay, here's something. So say S star is a strategy profile or strategy vector. So a strategy vector is basically, it consists of, in this case, if you have a 2-player game, so it's just S star 1 and S star 2. But S star 1 is a strategy of player 1 and S star 2 is a strategy of player 2. So this specific strategy vector, which in that case was confess and confess, is said to be in a Nash equilibrium if for every player I. Okay, so this notation S star of -I or S of -I means that you take out, or you just take out the ith entry and consider the rest of the thing as a tuple. So S1, S2, S3 till Si-1, then Si+1 till Sn. So you take out the ith entry and then you consider. So if you take out so here the payoff for this strategy is greater than taking out the ith entry from here and then comparing this with every other ith strategy that you have. Does everyone get it? So here, in the case of Nash equilibrium, what we did was, say I am analyzing this strategy. Okay? Here, so I claim that this is in Nash equilibrium. How do I prove that? I say that, okay, in this case, for player 1, for me, I have my outcome as -5. Okay, so my opponent has to, my opponent, I am, in this case I am assuming that my opponent confesses. I am assuming that my opponent confesses, and then I am comparing what I should do, or like what choices do I have. If I say, if I confess 2, then I have -5, which is equal to, you know, -5, and if I stay silent, I have -10, which is again less than like a worse choice than -5. So for me, this is a good thing. Then I consider it for player 2, which is the opponent. For him, he is assuming that you confess. In this case, he is assuming that you confess, and then he is considering his choices of staying silent or confessing. In one case, he has 0. Sorry. In one case, he has -5. In the other case, he has -10. So even then, this is my best. This satisfies that definition. So that is how we say that this is a Nash equilibrium. Now, the thing I said about having of both players having a strictly dominant strategy in a game means that if you, so in that case what happens is you can just eliminate all other strategies because they won't play them, and each of the players having only one strategy implies that this thing is an equilibrium, and that is the unique Nash equilibrium of the game. In this case, this confessing and confessing is the only dominant strategy. For this guy, confessing is the dominant strategy, strictly dominant strategy, and for this guy, confessing is the strictly dominant strategy. So we are left with only one outcome, and that is my Nash equilibrium. I'll give you an example. I have another game in mind where you would see that you don't have a strictly dominated strategy. So the thing about Nash equilibrium, the way of finding Nash equilibrium is as per our definition. Okay, so yeah, so if you have trouble understanding this very mathematical definition of Nash equilibrium, I would suggest that what happens in a Nash equilibrium is each strategy, the strategy of each player which is in the Nash equilibrium is his best response to the other strategies played against him. So there, in the previous prisoner's dilemma game, confessing was the best response to the other guy confessing. That is how we said that it's in a Nash equilibrium. Even for your opponent, confessing is the best response if you are confessing, right? Okay, so something that we will further see that multiple Nash equilibriums might exist, and it also might happen if you remember the game of matching pennies. It might happen that there is no Nash equilibrium at all. Now we will come to this, but first we see something that in that if you remember the prisoner's dilemma matrix, where you are rational, so you confess. Your opponent is rational, they have confessed too. So your outcome becomes -5 now -5. Both of you get a semester, both of you get a semester long suspension, right? But notice that if you guys had worked together, if you had trusted each other a little bit more, then you would have you have just gotten off with a detention. You both would have stayed silent, you would have got an outcome of -1, -1. So what this implies is that rational individual behavior that we assume in a game does not necessarily give you the common good, the common better outcome for everyone. You can apply this in the nuclear proliferation that we had after World War II, where you had USA and USSR, and both of them just keep making more and more nuclear weapons. So they might have, it was better for everyone if both of them had stopped, but then they did not trust each other, so they kept going to their Nash equilibrium. And yeah, so this explains pollution as well. This explains why your room is so much clean, and yeah. So as an example of how much time do I have? I would end in the next 5 minutes. There is one other game that I would like to stress is This is called the coordination game, or we also call it the battle of the sexes. And here, what we have is we have two people. We have a couple, Alice and Bob. So Alice loves going to the opera. Bob wants to go to the football game. But okay, they would rather be together. Like they would prefer being together than being separate. This is the premise of my game. How I model it is this way, in this form, that if both of them go to opera, then well, Alice is very happy. Bob is not as happy as he would have been in case he was there in the football game, but he is still happier than being, separated. So this is how we model this, and you can see that if you consider that Nash equilibrium definition, then look at this thing. So here, Alice goes to the opera, so her outcome is 2. If I am analyzing for Alice, then assuming that Bob goes to the opera, Alice's options are either 2 or 0. So 2 is a better thing. Then again for Bob, if you analyze this, okay, assuming that Alice goes to the opera, Bob has 2 options, either 1 or 0. So 1 is better option. So this is a Nash equilibrium. Similarly, this is again with the same logic another Nash equilibrium. So this game has 2 Nash equilibrium. Now okay, so something over here is that how actually so both of these equilibriums, but then how actually do you decide which one to go with? Well, you can just randomize, you can just text each other. Now this might look trivial. This having 2 different equilibriums and having to decide between them might look trivial in this case, but it is not so. In the example that I gave about the nuclear proliferation of US and USSR, that is a pretty serious matter. That is a pretty war situation that we can have. So in that case even you can have your representation as this. So here what happens is basically each country has 2 options. Either they choose to make nuclear weapons or they choose not to. So if both of them choose to make nuclear weapons, then well they are better off in their defense, but they are spending a lot of money and they are spending their money, manpower, the situation keeps escalating, so it's in general not that. So they are both with 2-2. If one had nuclear weapons and one did not, then the country did not, well, they would have been, we can mark them as 1, and the other guys would have had a leverage over the others. So they would have been marked 3. And the best possible thing over here that you can have is that, well, none of them produce nuclear weapons. In that case, the world is a better place. In that case, well, both of them, they can focus their highly expensive military budget to do some other things, to have better healthcare, for example. Then, okay, but notice that in this case, we are assuming something, that we are saying that this is a better outcome when we assume this very, luxurious assumption about the fact that they both trust each other. But, well, in the real life scenario, if you look at something that this happens, that if the US and the USSR first decide to not produce nuclear weapons, they don't trust each other. So an election happens in the US and they think that, well, the Soviets they might be in secret producing some nuclear weapons. So why not produce some yourself? So they would produce it, and then the USSR would have the same reaction. Either they get to know in some source, or they would, well, neither do they trust the US, so they would also prefer that, okay, let's have some nuclear weapons. And so both of them prefer this over this. This is how we get the name fluidity. So with this, almost the presentation is at the end. I would like to leave you with a few things that you get out from here. First is that we showed that chess is solvable in theory, but we do not just have the computational power for it. We talked about the game of Chom, and we know that a strategy exists, but we just don't know which strategy that is. So this is a favorite quote of mine. You might have heard it in some horror movie, but just because you can't see something doesn't mean it isn't there. Next thing what we learned was that the rational choices, the smart choices that we think we make don't always amount to the collective good. We saw that in the case of nuclear proliferation. We will, so game theory, as I said, that game theory is a very useful thing in modeling certain situations, starting from, well, the very basic games of chess and rock, paper, scissors, up till things like, well, evolution, politics, economics. So, for example, if you take politics for an example, then the various ways of having what do I call it? Like dividing the thing about divide and conquer, or the strategy of divide and conquer. That is so popular because, well, it works, and when once one player starts doing it, the other player also starts doing it, and then you just have people divided. But it gives you a nice equilibrium, so it works. So yeah, that was almost everything. Now, if you have any questions, you can ask. Thank you.
Perfect information and probabilistic game.
Perfect. Okay. So, perfect information and probabilistic. Imperfect. So, in imperfect information, what happens is that if say there are two players, the player 2 did not know what player 1's moves were, some of his moves were. In probability, the difference in writing it mathematically or stating that out mathematically is that there, well, a probability game can be perfect information. A probability game is not necessarily imperfect. For example, if I say that, okay, matching pennies, someone stated that how matching pennies, like what was the difference between tossing a coin and just choosing a side. So let's modify matching pennies, and you have a coin, you toss it first, you get whatever that thing was, what heads or tails. Then I see your heads or tails, then I toss it, I toss the coins, and I get either heads or tails. Then the rules are same as matching pennies. In the previous matching pennies case, I did not know what you were doing. Okay, that was imperfect information. Now in this version of it, it's perfect information, but there's an element of chance. So here, even by knowing what you are doing, I can't win, or I can't voluntarily win or lose. It all depends upon the chance of 50%. So you have basically, well, player 1. Okay, he has a 50-50 chance of heads or tails. Okay. Then, okay, so this is a position node for player 2. Then this guy has a 50-50 chance of a heads or tails. Similarly here. So here, getting both heads is now, it's now probability distribution of half into half. It's 1/4. There's a 1/4 chance that you will. Okay. So what the matching was that if head was there, then player 1 wins. If tail was there, then player 1 wins. In the other cases, player 2 wins. So for this case, it turns out that both player 1 and player 2 have a half of chance at winning. But if this game was say longer, if I would have done something like so if I would have added that Chom, if that game of Chom, if one is winning in this game, then you play chom, okay, and then that decides the winner. So basically, if there are two heads, then we play chom, okay. And if there are two tails, then we play rock paper scissors. That would have been a more complicated game in that case. So the difference being that there you can't just, your strategy can't give you a concrete outcome. In all of these cases, perfect, imperfect information, we said that our strategies mention exactly what we should choose. So in that sense, in this case, there are two players. So one strategy of player 1 and one strategy of player 2 would have combined to give you an exact outcome. In the case of chance, one strategy of player 1 and the other strategy of player 2 combines to give you a probability of what you can have. That is, in a sense, the difference.
What is information being
Okay, so in that, I'll just here, a strategy of player 1 can be choose heads. Strategy of player 1 is heads, just that. Strategy of player 2 can be tails. So, okay, in this case we can specifically write down so 30 seconds. So S1, S2, T1, T2 are strategies. If I say if I have any two strategies, each of one of player 1, one of player 2, say S1 and I have T2. So that gives me that player 1 chooses head, player 2 chooses tails. So that gives me a specific outcome. That if player 1 was to follow S1 and if player 2 was to follow S2, then the outcome for player 1 would be 1 and the outcome for player 2 would have been -1. But similarly, if I was here, then my strategy would not look like that. My strategy would look, so what I mean is, here 1, so the model looks like in this game that I said, player 1 does not make any decision. That is the difference. If I were to toss a coin, then the decision is not upon me. So I do not have a strategy in that sense. In this case, the decision lies upon the chance, the element of chance. So basically, if you remember that example that we toss a coin and then we play the game of chom, okay? In that case, we would model the game as, this is player 0, this is called nature. Let's say if the coin turns out to be heads, then my starting player is player 1. If it's tails, then my starting player is player 2. Then he does something, okay. whatever the game of chomp then proceeds with. So what I mean by chance is that this decision of having a head or having a tail, in this case if I try to formulate a strategy, if say I am defining a strategy for S1, fine. So S1 strategy would start from this node, not this node. In the end, what I get is that this, okay, so if my strategy, if the strategy that I am considering in the original game gives me some specific outcome O1, okay, then I will say that the probability that this thing happens is half. So my decisions start from player 1, not from player 0. That is the difference. Is that fine? Any other questions? Yeah.
What is strategy in a game of chance? Like, how can someone have a strategy in any chance game?
Okay. In any chance game, your strategy does not look like the definition that I showed you. In the definition that I showed you, what I told you was that explicitly, your strategy defines explicitly in each node of the game what you choose. In a game of chance, your strategy defines a probability distribution over that. So, if I have a strategy here, then in the case of a game of chance, when I am at this node, my strategy does not tell me what action to choose. My strategy defines a probability distribution over the set of all possible actions that I have, and then tells me which is the most probable choice.
But in cases like this, where the probability distribution is almost uniform, it is a binary.
Well, in case of this game, there's the probability distribution is uniform. It might
For
be
non-uniform cases,
in this case, it's like there is no point of defining something like this. But say I have three possible vertices that I decide from a lottery or something. It is biased. So one of my choices has a probability of getting chosen, say, well, 3/4. Then the other two are 1/8 and 1/8. So that is how the thing happens. Like that is how the probability distribution goes. In this specific case, I have taken it to be half, but that does not mean that there are games with only half probability. Fine. Anything else?
You mentioned that in the game of chess there are like 10 raised to 120 chess questions. Like, are they like randomly they are placing the chess pieces, or is it like
I honestly have no idea. I just know this fact that there is a paper, there exists a paper or an article, there's an article that devises a proof, like a proof, not a proof but a mechanism to approximate the number of possible chess positions. So I am not aware of how exactly they are calculated.